So this is an alternative approach to getting your link-based queue implementation up. So in this case, your collection is a circular linked list, which means at the end of the array, at the array of your queue, it links to the front of it. The only difference between this one and the previous implementation is that you're getting rid of this pointer, this very pointer that signifies the front is gone. Okay, and that is only the only saving. If you were to enqueue or dequeue something, let's say if you were to enqueue something, you'll basically you can add to the rare, but then you're gonna be performing at least 3 operations to sever. First of all, sever this connection, adding one node to it, and have this node points to the front of the queue, as well as adding this node, this rear of the queue to the new one. This is a new node. And then pointing this rear all the way here, okay? That's the only difference. For enqueue and dequeue means that you'll be getting rid of this. Let me just clear this. Dequeue means that you'll be getting rid of this and ensuring that the rear queue now points to this. So it's not as bad. Then again, the benefit is that you have you eliminate the use of the front pointers. So that is only difference here. And let's move on to the complexity analysis here. Now the complexity analysis here calls for storage and operations. So the storage size for both array-based and link-based are pretty similar. Remember that the array-based calls for the upfront allocation of the fixed size of the elements that you need, right? And that is the only kind of the unknown, because sometimes you don't know what you don't know, if there's going to be sufficient space or simply there is way too much space that you pre-allocated for array-based implementation. The link-based implementation, however, requires does not require any more space than necessary. So all you need to do is to have an empty link list to start with as your actual size of the queue, starting with 0. And the total amount of the storage allocation depends on how many elements you have, right, in the link base. Operational efficiency, both are O of 1. And the reason this is O of 1 is because we have both front and then rear, okay? So this is the front and then rear. And adding something to the end of your rear or deleting something pointed to by your front is O of 1, because you already know which part is the front, which part is the rear. Now, if you don't have front and the back pointers, then what's going to happen is going to have to do O of 1 in order to find out the end of the end of the list. That is very, very cumbersome. So typically we have both front and rear, and both operations are O of 1. Same thing with the array base, right? Since we have pointed to these things. As a matter of fact, these pointers for array base is just index, front index and the back index. For linked list is the physical node that points to these front and array references. So array base O of n, talked about that in terms of the element allocation. Linked list does not require anything to start with. The special case consideration is when array unbounded queue. So recall that the array unbounded queue is pretty cumbersome. It requires an enlarge method, right? Every time you need to double the size of your array, here is the added cost. This does not include in storage, right? But also does not include the need to do O of n copying, right? So you have to copy the old set of elements to the new one by unfolding, through use of your modulus, the indexing for the front and the rear to be represented anew in your new array. So it's costly considerations for that matter. Other than that, this is a summary, a pictorial summary of what it looks like when a queue is represented by a fixed size array, as well the fixed size arrays here, as well as by a link-based array, where you have both front and the back for both array-based and my queue. The difference between the two is the front and rear here is represented by the index. So these are just integers. These front and backs are actually the node itself. This allows you to point an empty object, which is a label for the front, and an empty object, which is a label for the rear, both pointing to a physical node as is, okay? But otherwise, everything else is pretty much the same. I'll say this is very, very efficient. This is not bad, but this has a drawback. You have to specify a fixed size to begin with. So it's typically when we're dealing with pre-allocation of memory without knowing how many elements that we have, it's just not a good idea, right? At runtime, you don't want to over allocate, you don't want to under allocate. So linked list implementation is the much preferred methodologies.